today I'll be introducing us to another concept which we've been alluding to severally in different ways. We've encountered this concept, even though we've not directly mentioned it, but we've looked at things that calorimetry have to do with. I'm sure some of you must have had a word that is similar to that, maybe calorimetry. So don't confuse those two. This is calorimetry, from calorie. And when you hear calorie, things that should come to mind should be energy. Another thing that should come to mind should be heat. So those are two words that should come to mind when you hear the word calorie or calorimetry. I'm sure many of us wear smartwatches or even on our track our movement, even on our cell phone, and it will show you the amount of calories you've burned and the rest, excuse me. So that is referring to energy. So that's what we'll be looking at today, calorimetry. So today I'm going to introduce us to this new chapter, but as we'll see, it is not entirely a new concept because we've alluded to this concept severally in other chapters. So that's what we'll be looking at today. And then as usual, as per the usual practice, the only way to consolidate a theoretical knowledge in thermodynamics is to carry out calculations. So towards next week, I'm going to ensure we go through the calculations. So it's either I have a pre-recording, which I upload for you, I'll let you know, or so it's either I do that or we do the same thing we did the last week rather, where we go through the calculations together in class. So please watch out for that. But definitely we'll be having calculations to consolidate this chapter, because without calculations, you cannot consolidate. I mean, it's not you cannot really do thermodynamics or understand the concepts in thermodynamics without calculations. So as I've mentioned earlier on, calorimetry has to do with measurement or estimation of heat or energy. That's what we've done. And a couple of things that you must have seen coming up every time, right from the beginning of the course, is the fact that reactions or processes take place under either constant volume or constant pressure. We would have seen that over and over. We'll see that coming to play again in this subject. So we'll see that coming to play in this subject, the fact that reactions or processes take place at under constant pressure or constant temperature. We've also seen, the different laws starting from zeroth law up onto the third law of thermodynamics. So who can tell me, if you're talking about heat, and we are talking about temperature, heat transfer or temperature change, what law of the three laws of thermodynamics, which law of thermodynamics, can you put that in the chat panel? Which law of thermodynamics do you think will guide heat transfer? Which of the laws of thermodynamics? Second law of thermodynamics. Why do you say so, John Matthews? Why do you say so? Second law of thermodynamics. Any justification for that? Because I'm assuming you didn't just guess it. So you can unmute yourself, John Matthews, or you quickly type it in. And if anyone else has a contrasting answer, you can give it to us. Okay. John Matthew is saying because it says that he transfers from hot to come to cold objects. Okay, partly right, John, but you're wrong in the sense that if you remember, that second law of thermodynamics, the emphasis on second law is actually about spontaneity. The fact that heat can only be transferred in that direction. So that is the emphasis of the second law. And remember, the second law wasn't just about heat, it's about general processes. So one of the processes is a transfer. So the second law, yes, it states that it stated, or it states what you've just stated, which is that heat transfer can only happen in a particular direction. It cannot happen in the opposite direction. But the emphasis, the underlying law that was a good attempt, John. That was, and it showed some thinking, so that's a good one. But it's the basis for calorimetry is the first law, which is the fact that energy can be transferred, energy can be transformed, but energy cannot be recreated. So energy can be transferred, energy can be transformed, but energy cannot be recreated. So it is based on the first law of thermodynamics, not the second law. So the only thing about the second law, as I've mentioned, is that it emphasizes on spontaneity, and also it supports the fact that energy can only move, heat can only, heat can only move from a place of high temperature to a place of low temperature. So take note of that. So the temperature change along with specific heat and mass of the solution can be used to calculate the amount of heat involved in a process. So we'll be looking at that. So a couple of definitions. I'm just going to emphasize on the three basic ones. You pick up the others in, there is a further reading that I've provided at the end of this class. As I'm going to make the class as short as possible, I want you to go through the further reading that I provided you at the end as soon as possible. So as we mentioned, calorie. So when you see calorie, it has to do with energy. So calorific value, the amount of energy. So when we talk about calorific value, it is energy measured after burning a fuel, and after burning a fuel, after burning any material, after burning a fuel or any material when you burn it completely. And when you talk about burning, what are the things that come to mind? One, combustion. Combustion only happens in the presence of oxygen. So we'll see later on that when we look at our calculations are based on oxygen and are based on hydrogen reacting with oxygen to form water. So take note of that. So when we talk about burning, we are talking about combustion, and combustion only takes place under what condition? In the presence of oxygen. And for the fuel that we are talking about, the materials which can either be gaseous or solid, these materials naturally must contain hydrogen. So take note of that. They must contain hydrogen. So when they contain hydrogen, they react with the oxygen in the air, or the oxygen, if it's pure oxygen that is used. The hydrogen and oxygen react, and then water is formed. So when this burning occurs and the water vapor, there is the reaction between hydrogen and oxygen. If what you are measuring in the product is in the form of liquid, meaning water in its liquid form, then what we are measuring is HCV, higher calorific value or higher heating value. So you see it as HHV in some cases, we see it as HCV in other cases. On the other hand, so in the HCV, so the thing that should come to mind then is, so if it's heating that is taking place, what that tells you is that what would actually come out is steam. So the form in which the water comes out is steam. So it's actually after condensation that then you can talk about water in its liquid form. So when you allow the steam, so you have the hydrogen in the material reacting with oxygen in the atmosphere, they come together, steam is formed, and when you allow it to condense, you're measuring the higher calorific value. But if you don't allow it to condense, you allow the steam or water in its gaseous form, you're measuring the lower calorific value. So it is essential to note this fundamental things so that whenever you're dealing with calculations, then you'll be able to know, oh, it's LCV I'm calculating or it's HCV I'm calculating. If you don't understand the fundamental things, you mix it up. So a bomb calorimeter. Obviously, when you hear about the word bomb, it's the word should come to mind is explosion, explosion. So we've got something so similar to a thermometer. So remember, if you remember, part of things we learned at the very early part of this course, we saw how a thermometer measures temperature. So we've seen the fact that temperature is different from heat, while heat temperature is just is it's a temperature is a parameter, is a factor. We've seen that heat is energy. Heat is energy. So for example, you're measuring your temperature in degrees C and Kelvin, while you're measuring your temperature in joules or other units. So while your thermometer is used to measure temperature, calorimeter is used to measure your heat. While your thermometer is based, the working of your thermometer is based on the zeroth law of thermodynamics. The working of your calorimeter, as we've mentioned earlier on, is based on the first law of thermodynamics. So take note of those differences. And then you see as we move on that in the working of bomb calorimeter, you actually insert a thermometer just to show you that the working, what a bomb calorimeter is doing is different from what a thermometer is doing. So I've mentioned the reason why it's called bomb calorimeter. I've mentioned that, and in the so please go through that the slide, the what do you call it, the website that I've provided you there to see more details. And then here you also see how the bomb calorimeter works. So let me quickly show you the picture and then we go back to how it works. So you're going to see an ignition coil. The yellow thing you see there, that is the sample. So you put in the sample, which can be gaseous, which can be solid. So you put in this sample, and then the ignition coil is there's a spark in the ignition coil. So if there's a spark, then the combustion starts. And also take note, outside, because you'll be seeing this in the subsequent calculation, outside is water. But don't confuse this water outside to the water inside. Remember I mentioned earlier on regarding the water inside, hydrogen in the material is released, reacts with oxygen in this atmosphere. And the oxygen, when the hydrogen and the oxygen come together, water is formed, which becomes heat. And then which becomes steam. And then if the steam is condensed, we are measuring higher calorific value. And then if it is not condensed, you're measuring lower calorific value. So take note of those two things. Another thing you want to take note of is from some of the concepts we saw that whenever you're dealing with a process in thermodynamics, there needs to be a boundary. There needs to be a boundary. And then you have a boundary within which the process is taking place. We talked about the system boundary. So in this case, you see there is a boundary here. So what you have outside here is a completely insulated system. it's a completely insulated system. What that means is, and if you remember, when we were looking at closed system, we looked at closed system, we looked at open system. One of the things we emphasize on the closed system, I believe, is that you can have it being generated inside. So for example, you have an isothermal process, you can have it being generated inside, but the heat doesn't come in or doesn't go out. So there is this barrier. So there is this barrier there. So take note of that. So please, so there is this barrier there. So as I've mentioned, go through that fully. So I've given you an overview of how the bomb calorimeter works. Why it's called a bomb calorimeter? Because of the explosion that takes place inside. How does the explosion take place? There's an ignition inside. There's a combustion. When the combustion takes place, hydrogen in the sample reacts with oxygen in the atmosphere, and when that occurs, there is steam generated. And when the steam is generated, your you're measuring you're measuring your calorific value. So take note of that general description that I've given, but please ensure you go through the details in the websites that I've provided you there. So as usual, we'll be looking at this more critically when we look at the calculations that I've mentioned earlier on. So you want to take note of the equation, but what is essential in the equation is you need to know the notations, meaning what does each stand for. That's one. What is CV? What is this? What is that? Second thing you want to take note of are the standard units. We can never overemphasize that. We'll always talk about that standard units. So those are things we want to emphasize. And I want to take note of this. You see that this is not C with subscript V that we've been looking at, which is a counterpart of CP. You remember CP, we've seen CP, which is specific heat capacity, at constant pressure, or yeah, we looked at that based on pressure, but we have CV, which is based on volume. So don't confuse this with that. So they are not the same. So take note of that. They are not the same. So the CV here, that is a calorific value. And then, so that is the calorific value, not the CV we've encountered before. So take note of those. And then we've talked about, this says actual, so I need to take that out. Okay, so then um, we have the other values. Change in T, you should know that by now. Higher temperature minus lower temperature. So that is your temperature rise. So temperature rise. And then you have the mass of fuel, the sample. We've talked about that earlier on because you put in a sample. So when we have the calculation, these are the things we'll be looking at. Remember, I've alluded to there's a water, there's water, there's a water bath. So you remember looking at this, that's why this amount of water is usually bigger than that. You can see this is tiny compared to that. So you have that water equivalent of apparatus, you have this as well. Because the water equivalent of apparatus, how does that work? If you remember your Archimedes principle, when you submerge, so this apparatus has been submerged in that water. So it means that there's the space that this occupies. So the space that this occupies, that is the water equivalence of apparatus. So I'm trying to explain this so that when we look at the calculations, it will be clearer. So initial temperature so from this we can now calculate a change in T. And then cooling correction, so we'll see how that comes to the fore when we start looking at our calculation. So I'm just trying to explain this to us so that when we walk through the calculations and looking at this, if our heat capacity, is in kilogram Kelvin, what we want to ensure is during our calculation, everything here is converted to Kelvin. So take note of those so that I go through the when I go through the calculations, it will come easier. So the higher and lower calorific values are related. Can someone tell me, based on what we've talked about earlier on, why would this happen? Why do you think we have this? Can someone, you can either write that or unmute yourself, especially this part, the fact that it is LCV is equal to MCV minus mass of water formed, mass of water formed. Can someone tell me why that is the case based on what we've looked at? Can any takers? Why do you think it is the difference is based on water formed, based on what you've said? You can either unmute yourself or type it out in the chat panel. Any takers? All right, so no one is giving any response. So that will be based on the fact that what I've mentioned earlier on. Remember, we've said we talked about how the difference between the two. We talked about the fact that for at HCV, the water must have condensed to liquid. Under HCV, the water must have condensed to liquid. Under LCV, it is still steam. So that is why we've got that. And then remember, I've mentioned this a number of times today already. The fact that we look at hydrogen. Hydrogen is contained in the material. So one of the formulas we'll be working with is this Dulong's formula. So Dulong's formula. So you have the Dulong's formula, and then one of the things you must have learned from, I believe we've learned from what we did in the previous chapter is coefficients. We alluded to the fact that you've got coefficient values. So take note, the elements that are involved, that we look at, that are involved in combustion in any material. So different materials have been taken, different fuels. So talking about fuel, it can even be your petroleum. Actually, for all the petroleum, I don't know if I mentioned it in the class before. One of my main research area is renewable energy. So whenever you're dealing with anything that has to do with energy, your biodiesel, your biogas, your normal diesel, your petroleum, one of the ways to characterize your fuel is to calculate the HCV. So calculate the HCV. And the three main components, there can be other components. For those of you, not those of you, I believe you all did CPI. If you remember in CPI, we said the main components of your hydrocarbons, of your fuels, are carbon, and hydrogen. We also said you have some oxygen, and if you remember, we also mentioned the fact that you've got some sulfur present as well. So that's why in this calculation, these three main elements are incorporated, and in front of each of them, what we've got is let me just change that. So what we've got in front of each of them is their coefficients. So in front of each of them is their coefficients. So you've got a coefficient in front of each of them. So we have this coefficient for that. We have there is one here for hydrogen. So, and then you have this 144 that deals with caters for all of them. So you have, and the coefficients represent the higher calorific values of the respective constituents. So we'll see there. We've seen this. This term gives the amount of hydrogen available. Remember, I mentioned earlier on, there is always hydrogen in the fuel. there's hydrogen in the fuel. And then we said the hydrogen in the fuel reacts with oxygen. And when that the hydrogen in this reacts with that, you have your H2O forming, H2O, which can either condense or be as steam. So we've talked about that. So things will be clearer when we look at the calculation. So here's another example. We'll be looking at um, later on. So calorific values of gaseous fuel. So take note. So how we calculate for solid fuel, and the rest is different from how we calculate for gaseous fuel. So what we look at here, we'll be looking at example 9.3. What we'll see, for example, example 9.3 is we will be looking at where is their coal. So the code is solid. But in the next example, in the next thing, we'll be looking at for a gaseous material, a gaseous fuel. So I've alluded to that earlier on. Your biogas, for example, that is a gaseous fuel. There are other gaseous fuel as well. Your hydrogen itself. That is why for any material to be able to combust, it must have hydrogen in it, and then there must be oxygen in the atmosphere before that can occur. So you see, for this example, we'll be dealing with, so for one example, we'll deal with solid. For the other example, we'll deal with liquid. And also remember, one of the things that I've mentioned earlier on, issue of, we've talked about this standard, this and that, but those things will get clearer in the example. I mentioned CV, how CV shouldn't be confused with the C and little v. And then CP, we've mentioned that already. So we'll be seeing that more clearly as we move on. All right, so same story as I mentioned. You'll be given water circulated and the rest, and so this will be looking at these different values and in the calculation. I've mentioned what the water circulated is. I've mentioned the issue of the temperature, how you calculate temperature change from this. And looking at this, if it's talking about condensed steam. So looking at this, we have condensed steam. That means we can look at condensed steam, and then we can look at condensed steam will be what? The water in the liquid form. So but when you look at the calculation, it will become clearer. And looking at this, it shows us that we'll be able to, based on what we've seen earlier, we should be able to calculate the LCV and HCV. So please, there's an extra reading that I've inserted there for you to look through. Any questions before we adjourn the class?